Hello again and welcome to tutorial number 23, drill 18. In this tutorial we're going to be talking about radio receivers. Before we kick off with receivers, how about we do a little bit of revision on transmission? Not the block diagrams, but actually what is taking place. We've got a voice frequency range of 0 to 3 kilohertz. That's the usual voice frequency range used on amateur radio, and that range is prescribed by regulation. An entertainment station would use a much wider bandwidth than 3 kilohertz. Anyway, this 0 to 3 kilohertz will not radiate from an antenna unless the antenna is extremely long, because the wavelength of audio is extremely long. In fact, such an antenna we call a telephone line, so we wouldn't bother. In radio, what we do is take our voice frequency range and translate it to a radio frequency by mixing it in the transmitter with a radio frequency carrier. I've chosen a nominal carrier frequency of 7,000 kilohertz. The voice frequencies are translated to two bands of frequencies, the lower sideband and the upper sideband. Now, what's happened is that these voice frequencies have just been moved in frequency to radio frequencies. So if we could see all the little undulations, all the voice frequency changes there, we would see them here as well. The only difference is that this is an exact map of the voice frequencies at radio frequencies. So all we've done really is a frequency conversion from 0 to 3 kilohertz to two pairs of radio frequencies. One is called the lower sideband, that's 3 kilohertz wide. The other is called the upper sideband, that's 3 kilohertz wide. For example, the high voice frequency, 3 kilohertz, would be translated to that frequency on the lower sideband. Say there was a frequency here on 2 kilohertz, that would be translated to a radio frequency about there. So all of these voice frequencies, and we just draw a rectangle rather than draw all the little signals, but these are all the little tones and frequencies in our voice, are simply translated to a radio frequency. And with double sideband, that happens twice. With double sideband, we mix the voice frequencies with a carrier, and we produce both sidebands, an upper sideband. This is an exact representation of these voice frequencies, and the lower sideband is an exact representation of these voice frequencies. Now this whole signal is radio frequency. It goes from 6997 kilohertz, which is 3 kilohertz down from the carrier, 3 kilohertz, and 7003 kilohertz, which is 3 kilohertz up from the carrier. So all we've done is converted our voice frequency range to a pair of radio frequency ranges, and in double sideband full carrier we still have the carrier there. So if we were to receive this signal on an antenna, we need some sort of device, a frequency converter, I'll just abbreviate that. If we had a frequency converter, we could simply put this signal into the frequency converter, and we could convert back to audio frequencies, back to audio. Now remember, in the transmitter we did the mixing by using a nonlinear device. So if we're going to do another frequency conversion from these radio frequencies to audio, and that's what radio reception is all about, we're going to need a nonlinear device as well. So the purpose of this slide is just to show you, or remind you, that radio transmission is really just about frequency translation and amplification. We've translated our 0 to 3 kilohertz voice frequencies to two pairs of radio frequencies, and we haven't lost any information or intelligence in those radio frequency signals. If we want to get that audio back, we need to receive this double sideband signal and go into a frequency converter which will convert it back to audio. And with double sideband full carrier, there's a very easy way to do that. This slide, which is pretty much the same as before, except I've added a double sideband receiver, and it's a full circuit of a double sideband receiver. That's all we need to receive a double sideband signal. Let's have a look at what we have. And remember, what we're trying to do is translate these radio frequencies back to audio. That's our purpose. We need a method of picking up the radio signal, so we have an antenna. Antenna would be approximately resonant on 7,000 kilohertz. We then have a parallel tuned circuit, and it will be resonant on 7,000 kilohertz. Remember, well, you don't need to know this for your exam, but I'm going to give it to you anyway. The resonant frequency of that circuit, that LC circuit, FR equals 1 over 2 pi square root LC. So we designed this circuit to be resonant on 7,000 kilohertz. When we do that, this tune circuit, this parallel tune circuit, acts like a bandpass filter, and only signals on 7,000 kilohertz can go through the antenna and pass through to the rest of the receiver. It only passes 7,000 kilohertz. Won't be examined on any of this. I'll tell you what you'll be examined on, and that's the drill questions, or questions similar to the drill questions. But this is very helpful in understanding radio communications, and particularly reception. So what we've done so far is the parallel tune circuit and the antenna has selected this radio frequency signal from all the other radio frequencies that are present in the Earth's atmosphere. So what do we do now? Well, what if we put the signal into a nonlinear device? Now, a good nonlinear device is a diode. A diode doesn't amplify, but a diode only passes current in one direction. And the forward, if we were to put voltage, if we were to graph voltage and current, I might be off screen there. If we were to graph voltage and current for a resistor, so we put voltage across a resistor and monitor the current and do a graph of current versus voltage versus current through a resistor, we would get a straight line, because a resistor is a linear device. If we were to do the same thing for a diode, if it was forward biased, we get something like this. It's nonlinear. A diode is a non-linear device because the current is not proportional to the voltage, whereas with a resistor it is. So a diode is a non-linear device. For those of you that haven't recognized it, this is the schematic diagram of a crystal set. In the old days, they used to use a galena crystal for the non-linear device. These days, we use a germanium diode for the non-linear device. But the point is, it could be any non-linear device. A diode doesn't amplify, so we could have an amplifier here which is operating in non-linear mode. So we would get two things from the amplifier. We'd get non-linearity, which we need for mixing, and we would get amplification. But here we're just doing the simplest thing we can do and use the diode as a nonlinear device. So what's going to happen is that this signal is going to mix in that diode. If I'd wanted to, I could have drawn a rectangle here and just put a mixer. Let's have a look at what's going to happen when this signal mixes in this diode. This circuit ahead of it, all it does is select this signal, nothing else, and the diode is now going to mix that signal, and I'd like to talk to you about what happens when that mixing occurs. Now remember, we've still got our carrier here on 7,000 kilohertz. This is double sideband, full carrier. Very inefficient mode because 50% of the power is in the carrier and 25% is in each of the sidebands. Okay, if this signal from 6997 kilohertz to 7003 kilohertz goes into a mixer, a nonlinear device, a diode in this case, what's going to happen? Alright, well let's just try a few things. What is the difference between 7,000 kilohertz and 7,003 kilohertz? There's a signal here on 7,003 kilohertz, and there's one here, that's a radio frequency signal, and there's a carrier on 7,000 kilohertz. The difference between 7,000 kilohertz and 7,003 kilohertz is 3 kilohertz. The difference between the, say, 100 hertz, if we just go into the upper sideband a little bit, the difference between the carrier and this frequency in the upper sideband will be about here. Maybe almost 0 kilohertz. Almost, not quite. And each radio frequency signal in there will be converted to a difference frequency, the difference between 7,000 and all these individual frequencies, and I'm going to draw them in. But it would be easier if I just drew a rectangle, and it would be even easier if I drew the rectangle that I have above, because that's exactly what it is. By mixing the carrier with the upper sideband, we're able to convert the upper sideband to audio. Similarly, when we mix the carrier with the lower sideband, we convert the lower sideband to audio as well. So that is how the crystal set works. Of course, there will be at the output of the mixer, there will be some radio frequency signals that we don't want. So we put a capacitor there to bypass those radio frequencies to Earth. And so what we're left with in our headphones is just audio. So that is how the old crystal set worked. A tune circuit to select the desired signal and an antenna, and then we need to mix, because it's double sideband and we have the carrier, we need to mix the carrier with the sidebands in any nonlinear device, and as a result of that mixing, the upper sideband and the lower sideband are converted back to audio, which we can hear in our headphones. I used to build these as a child, and I would not use headphones. I would take the headphones out, and you can put a small audio amplifier in there, and drive a loudspeaker. Such a radio receiver is not very selective. That's an audio frequency amp, and we could connect that to a loudspeaker, and we could hear the radio station. And that's a very simple circuit, or you can buy a little kit. I recall from doing this on the broadcast band that I used to use a cardboard tube from a Cool Mint tin, and I'd put, I think it was 60 turns of wire on the coolment tin, and that capacitor needs to go from roughly 30 to 250 picofarads, variable capacitor, airspace capacitor, and that puts that puts this tune circuit on the broadcast band, not 7,000 kilohertz. In fact, the values that I used for the inductor was 100 microhenries, and the capacitor, I think it was 200 or 250 picofarad, one or the other. But if you use the equation FR equals 1 over 2 pi root LC, you'll find that that pair, this pair here, would be resonant on around about 1 megahertz. But in this circuit, we would have it resonant on 7,000 kilohertz. A double sideband we've learned is not the way to go anymore. It's useful to understand how single sideband works, but double sideband is a very inefficient mode of transmission. What we normally do these days is use single sideband. The carrier is suppressed in the balance modulator, and one of the unwanted sidebands is removed. So what we end up with is a suppressed carrier, so it's gone virtually, and the bandpass filter after the balance modulator will either pass the upper sideband or the lower sideband. So now we've got a problem. Now we're only transmitting just the upper sideband or just the lower sideband, and we're not transmitting the carrier, so we can no longer use a crystal set. With double sideband, we have the carrier present at the receiver, because the carrier is received by the receiver along with the upper and lower sideband, so the carrier is present to mix with each of the sidebands to produce audio. When we transmit just upper sideband or lower sideband, the method of converting that back to audio is a little bit more complicated. And again, this is not examinable, but it'll help you understand and help you remember how SSB reception works. So let's have a look at how we could convert just a single sideband without a carrier back to audio. Well, we've replaced our double sideband transmitter with a single sideband suppressed carrier transmitter. Audio is the same, 0 to 3 kilohertz. But now we're only transmitting one sideband, and I've chosen the upper sideband. It's the same principle exactly for the lower sideband. And we no longer have a carrier. So we are still, this is our receiver, and the receiver is very simple. It's used today. It's called a direct conversion receiver. It's called direct conversion because we're going to convert this upper sideband back to audio in one step. The direct conversion receiver is also known as the homodyne receiver or the zero IF receiver or just DCR receiver, direct conversion receiver. They're still used for simple telegraphy transmitters. A direct conversion receiver is quite good, but there are better receivers. The purpose of this tutorial about the direct conversion is so you can understand easier the super heterodyne receivers that we'll be talking about in a short while. So our radio frequencies, which go from 7,000 kilohertz to 7,003 kilohertz, we're going to have a band of radio frequencies. Exactly what I've got there. That's what's going to go into there, and it's going to go from 7,000. The bottom of the upper sideband is 7,000 kilohertz. The carrier's not there. And the top of the upper sideband is 7,003 kilohertz. Now suppose at our receiver we had an oscillator on 7,000 kilohertz. Well, that oscillator is on the frequency that the carrier used to be on. That oscillator is at the bottom of the lower sideband. Now it wouldn't matter if we frequency translated this to 14 megahertz or 28 megahertz or 100 megahertz, the carrier would still be at the bottom of the lower sideband. So if this is an upper sideband signal without a carrier, we need to put the carrier back where it would be, and the carrier would be here on 7,000 kilohertz. So this local oscillator, this beat frequency oscillator it's called, in the receiver is how we tune in the radio stations. So if we put a 7,000 kilohertz signal into this mixer and we mix it with 7,000, so the bottom part of the upper sideband signal will mix with 7,000. What's the difference between 7,000 and 7,000? It's 0. What's the difference between 7,003 kilohertz and 7,000 kilohertz? It's 3 kilohertz. Can you see that what we've done is converted the upper sideband, which was a radio frequency from 7,000 to 7,003 kilohertz, by putting that into a mixer and a BFO on the frequency of the carrier where it would be if it was still there. We put a BFO on the frequency of the carrier on the frequency the carrier would be if it was still there, and that will mix with the upper sideband to produce our audio frequency range, and we will hear that in the speaker. The audio frequency amplifier will not pass any of the other RF mixing products, so we don't have to worry about them. Audio frequency amplifiers only amplify audio frequencies. That's called a direct conversion receiver. It has problems, because if we were receiving a signal on, say, 144 megahertz, our BFO would need to be on 144 megahertz. If we're and having oscillators so high in frequency makes them quite unstable. And for amateur radio purposes, direct conversion receivers are really handy for simple little receivers to monitor transmissions on, or for Morse code reception. But because the BFO has to be, which is just an oscillator, has to be on such a high frequency to receive high frequency signals, the BFO tends to drift and they tend to wander in frequency a little bit. So they're not that popular in more sophisticated amateur radio equipment. You will not see a direct conversion receiver. But I would like you to understand that. You won't be assessed on it, but if you do understand this, you're going to understand much easier super heterodyne receivers used for the reception of single sideband. We're simply, in this receiver, we're simply taking our radio frequency sideband, which is still 3 kilohertz wide, same as the audio, and we're putting the carrier back in on 7,000 kilohertz, and that carrier on 7,000 kilohertz coming from the BFO, that's in the receiver, this is all in the receiver here, that will convert the upper sideband in one step back to audio, and we can listen to it. It works okay, but it's not the most sensitive or selective receiver. Sensitivity is a name given to a receiver's ability to pick up weak signals. Selectivity is a name given to the receiver's ability to receive only one signal that's on the frequency it's tuned to and to reject all other signals. Direct conversion receivers aren't particularly sensitive or selective, but they're very, very useful, simple receivers. The slide shows the block diagram of a double sideband super heterodyne receiver. To be more specific, it's a single conversion receiver, but we'll get to that shortly. The super heterodyne receiver was invented by Major Edwin Armstrong, very, very clever radio genius, and it's still used today in most amateur receivers and transmitters. Let's have a look at it. Last time we converted our double sideband signal or our single sideband signal. We used a crystal set to detect or to modulate our double sideband signal, and we used a direct conversion receiver to receive single sideband. Both of those are not very practical receiver systems. This one is. And let me just go through it and then we'll talk about it. First of all, I've changed the frequency to 1200 kilohertz. There's no reason for that. Just an easier figure to work with, because all the frequencies remain relatively the same. If the carrier is on 1200 kilohertz, then the upper sideband is 3 kilohertz above that, and the lower sideband is 3 kilohertz below that, each sideband then being 3 kilohertz and the total bandwidth being 6. With the super heterodyne receiver, we have an RF amplifier. By the way, this is on the broadcast band, and on the broadcast band they use much wider bandwidths than 6 kilohertz, but these are just sample numbers for our purposes, because on amateur radio bands 3 and 6 kilohertz are the typical bandwidths used for amplitude modulation. So in this receiver, this is the signal that we're receiving. The output from a double sideband transmitter has a carrier and 2 sidebands, and it's being received here. And this is, if this were a receiver designed to cover an entire band, then this RF amplifier would amplify the entire band. So if this was the broadcast band, this amplifier would have a bandwidth of around about 1.5 megahertz or 1.6 megahertz. Roughly. So a lot of signals are going to come into the RF amplifier, not just the signal we want on 1200 kilohertz. 1300 kilohertz is going to go into this amplifier and be amplified. 500 kilohertz is going to go into this amplifier and be amplified. So this is just a broadband RF amplifier with a bandwidth equal to the band that you're operating on. Now, Edwin Armstrong's idea was to do a frequency conversion of the incoming signal, no matter what frequency the incoming signal was. So if the incoming signal was 100 megahertz, 500 kilohertz, 4.4 megahertz, it doesn't matter. His idea was to take whatever the incoming signal was, this signal, and do a frequency conversion. Here we have a mixer and a local oscillator. It's called the local oscillator because it's local to the receiver. This is practical, by the way. You'll still find this in many receivers today. So his idea was to take any incoming signal and then use a frequency converter, a mixer and an oscillator to convert that signal to a standard frequency called the intermediate frequency. And one of the most popular intermediate frequencies is 455 kilohertz. This amplifier, this intermediate frequency amplifier, will have a lot of gain, a lot of amplification, and a lot of selectivity. So this receiver is going to be very sensitive and highly selective because this amplifier, this IF amplifier, is specially tuned to 455 kilohertz. It might have bandpass filters in there as well to increase its selectivity. So it has high selectivity and high gain. That gives our receiver high sensitivity and it gives us high selectivity. It gives us the ability to receive one signal only and reject all others. Then we have a detector. This is where we're going to do our mixing to recover our audio. So what we're going to have at this point is a double sideband signal with the carrier on 455 kilohertz, and when it goes into the detector, the carrier on 455 kilohertz and the upper and lower sideband will mix, and one of the mixing products will be the recovered audio frequencies. Now, if we want to convert 1200 kilohertz in this mixer to 455 kilohertz, we have to put this oscillator on a frequency that will do that. And the normal practice is, because there are a couple of frequencies we could put the oscillator on to convert 1200 kilohertz to 455, but the normal practice is to put the oscillator on a higher frequency than the incoming signal. So if we were to put the local oscillator on 1200 kilohertz plus 455 kilohertz, that would be 1655 kilohertz. Let me write that in. It'll be a bit rough because I'm drawing with pen. If we put the oscillator on 1655 kilohertz, now we don't know the frequency of the oscillator on a broadcast band receiver. This is the dial on the radio, and it's not marked in frequency. If we were going to, if this was the radio band, and we've got 4AY here, I'm making this up. That's station 4AY, that's station 4BC, whatever. When we move the tuning dial on the receiver, we're changing the frequency of this oscillator. And if, let's say 4BC, station 4BC was on 1200 kilohertz. When we adjust the knob and move the frequency up to 4BC on the dial, the local oscillator will be on 1655 kilohertz. The user doesn't know that, but you need to know that because you're a radio amateur and not a domestic user of receivers. The domestic user just turns his tuning knob to 4BC, which is on 1200 kilohertz, and that probably says 1200 kilohertz on the dial. If it does have frequency on the dial, that means that you're receiving 1200 kilohertz. But when we do that, we're actually putting the local oscillator on 1655 kilohertz, because the difference then between the incoming signal and the local oscillator, when they mix in there, if we called the local oscillator F1 and we called the incoming signal F2, then one of the mixing products, F1 minus F2, that is 1655 minus 1200, is going to be 455 kilohertz. So we're going to frequency convert our incoming signal to 455 kilohertz. And it doesn't matter what frequency the incoming signal is. If we want to listen to a different signal, we now have to change the local oscillator so that the difference between the local oscillator and the incoming signal is 455 kilohertz. The really big advantage of that is that from here on, every radio is the same, because we're always doing a conversion from 1200 kilohertz to the first IF. This radio only has one IF. We'll show you one that has two IFs shortly. And from then on, this is a stock standard receiver. The first IF amp on 455, the detector, which is just a nonlinear device. It could be just a diode, which is a nonlinear device. This stage could be just a simple diode and an audio frequency amplifier to drive the loudspeaker. That's a single conversion super heterodyne receiver. If, for example, we wanted to receive 1300 kilohertz, what would we do? Right, suppose we didn't want to receive 1200 kilohertz, we wanted to receive 1300 kilohertz. If we had our local oscillator where it was before, on 1655 kilohertz, we wouldn't be able to receive 1300 kilohertz because the local oscillator on 1655, F2 minus F1, the local oscillator is F2, frequency 2, the incoming signal is F1, and the conversion is F2 minus F1 must equal 455 kilohertz, otherwise we don't hear it. So if we're on 1300 kilohertz and we want F2 minus F1 to be 455 kilohertz, then the local oscillator would have to be on 1755 kilohertz. And now we'll receive a station on 1300 kilohertz, because the difference between 1300 kilohertz and 1755 kilohertz is 455 kilohertz. So we're changing frequencies by changing the frequency of the local oscillator to convert the signal we want to an IF frequency of 455 kilohertz. And in every radio, this remains the same from then on, because we're dealing with the same signal from that point on. In the detector, the signal now at this point is on, the carrier is on 455, and the IF amplifier has given us a great deal of gain and a lot of sensitivity, and we still have an upper and lower sideband. And a lower sideband, I'll just do an L for that. But it's on 455 kilohertz, and when that goes into the detector, which is a nonlinear device, the carrier on 455 kilohertz mixes with both the sidebands to produce audio frequencies, which we hear in the loudspeaker. It's not that hard, is it? The principle is to convert the incoming signal to a standard frequency called the intermediate frequency, and a common intermediate frequency is 455 kilohertz. Now, before I forget, these intermediate frequencies are protected. There are a number of intermediate frequencies, and you certainly wouldn't want someone using a transmitter on 455 kilohertz, because if you did, this IF amplifier would pick up that signal and you would hear interference. During the Second World War, the radio jammers used to transmit signals on 455 kilohertz, because that would go straight into the IF amplifier of the superheterodyne receiver and cause interference and prevent reception. Now, for all their advantages, single conversion superheterodyne receivers have one disadvantage which you must know about. Their advantages far outweigh the disadvantage. The disadvantage is this: we're wanting to receive a signal on 1200 kilohertz, and to do that we have to put the local oscillator above 1200 kilohertz by an amount equal to the IF, so that the difference between the wanted signal and the local oscillator is 455 kilohertz. The difference between 1200 and 1655 is 455. But there is another signal that can, if it's available, if the signal is present at the antenna, that signal will also be converted to 455 kilohertz. And that signal is called the image frequency. And it's a disadvantage and a problem with superheterodyne receivers that we can easily overcome. And we'll talk about how we overcome that shortly. But you do need to know this equation. The image frequency is calculated by the signal frequency. This is the signal frequency, plus or minus 2 times the IF. And in this case, I'm taking plus. So the image frequency equals 1200 plus twice the IF, which is 910. 1200 plus 910, I hope, is 2110 kilohertz. You need to remember this equation. Image equals the signal plus or minus twice the IF, and the signal is 1200 kilohertz. The IF is 455, so that becomes 910 plus 1200 is 2110 kilohertz. And this is an unwanted signal. We don't want to receive this signal. But what happens if it does arrive here? What if there is someone transmitting in the area on 2010 kilohertz? And we're listening to 1200 kilohertz. Well, if a strong signal arrives on 2010 kilohertz, It will of course go through the RF amplifier because it's in the band. It's close enough to this band. This is a broadband amplifier, so it'll probably get through the amplifier. If it was further away, if it was megahertz away, then it wouldn't get through the amplifier and it wouldn't be a problem. But in this case, this unwanted signal is not too far away from our wanted signal. Can you see that 2110 kilohertz will mix with our local oscillator on 1655 kilohertz to produce 455 kilohertz, because the difference between 210 and 1455 is 455. So this is an unwanted interfering signal which will also be converted to the IF frequency by the local oscillator. We want to convert 1200 to 455, and it does that nicely. The difference between 1200 and 1655 is 455. That's what we want. Unfortunately, if there is someone transmitting nearby on 2110 kilohertz, it will also mix with the local oscillator to produce 455 kilohertz, and that will interfere with our station on 1200 kilohertz. That's called image interference, and we need to somehow do something to a superheterodyne receiver to make it stop doing that. It's not a serious problem, but it's a problem nevertheless. And you do need to know about image interference and how to calculate it. And later on, and I've shown you here, and later on we'll be going through a lot of sample questions and doing quite a few of these in the drills. You'll notice some changes to the block diagram in this slide. I've added a second. Here was our first mixer. That before we only had one mixer, one local oscillator, and one IF. I've added a second mixer, a second oscillator, and a second IF. The difference is I've made the first IF 10.7 megahertz, and that's also a protected IF frequency. No one's allowed to transmit on 10.7 megahertz. And the second IF is 455 kilohertz. So we now have two IF amplifiers. One is a high frequency IF on 10.7 megahertz, and one's a low frequency IF on 455 kilohertz. IF amplifiers are good. You might think we're going to a lot of trouble here using all double conversion. This is called double conversion because we're converting twice. If we were converting 3 times, if we had 3 IFs, it would be a triple conversion superheterodyne receiver, and that's certainly not uncommon. But double conversion is very, very common. What we're doing with what we did with a single conversion is we took our wanted signal and we frequency converted it to 455 kilohertz. Now we've got double conversion. We're going to take our wanted signal and we're going to receive it in a broadband RF amplifier. That amplifier will amplify the whole band, but it won't amplify things megahertz away. It'll just amplify a narrow band of frequencies, maybe a few hundred kilohertz. And then we're taking our 1200 kilohertz signal, placing it in the mixer and oscillator. That, remember, the combined function of those stages is as a frequency changer, or a frequency converter, or if you like, a frequency translator. They just change the frequency. So 1200 kilohertz comes through our RF amplifier and we change its frequency to 10.7 megahertz. It's a big change from 1200 kilohertz up to 10.7, but it hasn't changed the signal at all. It's still a double sideband signal. It still has an upper sideband 3 kilohertz wide, a lower sideband 3 kilohertz wide, except the carrier is now on 10.7 megahertz. We're going to give it a lot of amplification. Then we're going to go into a second mixer, an oscillator, that's another frequency converter, and convert to 455 kilohertz. And then we're going to go to our detector or demodulator. Detector is also called a demodulator. And that will mix at this IF amp here. The carrier is now on 455 kilohertz. with an upper and lower sideband, and they will mix just like in the receiver before. The difference between the carrier and each of the sidebands is audio, and we listen to our double sideband signal coming out there. So using two IFs is good because it gives us more selectivity and more sensitivity. Sensitivity is the ability of a receiver to detect weak signals, and selectivity is the ability of a receiver to reject unwanted signals. But what is our 10.7 MHz IF going to do for us in terms of image? Remember, the equation for image is image frequency equals the signal frequency plus or minus twice the IF. Well, twice the IF is now 21.4 megahertz. And then you've got to add on the signal. So any image appearing here is going to be megahertz away, and the RF amplifier is not going to allow signals megahertz away from the desired signal to come through. So that eliminates the image problem. There is no image problem with a double conversion superheterodyne receiver, which will always use a high frequency IF as the first IF. And the purpose of using the high frequency first IF is to place the image so far away from the wanted signal that it is no longer a problem. That's why we use double or even triple conversion. But double conversion does away with the image interference problem altogether. The first oscillator is still how we change frequency. If we want to tune to a different frequency other than 1200 kilohertz, we would change the local oscillator. This oscillator is always converting 10.7 megahertz to 455 kilohertz. So this oscillator doesn't have to change frequency, so it would be a crystal oscillator. So there you have it, a double conversion superheterodyne double sideband receiver. Later on we'll be talking about single sideband and single sideband receivers, and it's going to be an easy addition to what's on this slide at the moment. Later on, probably in the next tutorial, I'm going to be going back to that block diagram of the SSB transceiver. Not that you need to know it, but I just like to put these block diagrams into some sort of context by looking at a practical single sideband transceiver for amateur radio. But probably in the next tutorial, because we still need to discuss single sideband reception, and that will be in the next tutorial. So I'll see you then. I would advise you to perhaps take a screen grab of this and print it. If you've got a software program that can capture the screen, you can do that and print it. Or in Windows 7 there's the clipping tool that you can use. Just start and type in clipping tool, I think you'll find it. Just capture that screen, put it into a paint program or word processor and print it, because it's a handy little diagram for you to have about the operation of a superheterodyne double sideband AM receiver. Cheers for now. This is Ron, VK2DQ. I'll see you in the next tutorial.